Okay, so this short video is on eigenvalues and the eigen decomposition, or what is sometimes called the spectral decomposition of matrices. So let's start with what eigenvalues are. So this should be familiar to all of you, I hope. So let's suppose A is an n by n square matrix. Then we say that X is an eigenvalue. X is an eigenvector of A corresponding to eigenvalue lambda if AX equals lambda X. So if we think about A as a transformation, the eigenvectors of A are the directions in our input space that are unchanged by the transformation A. So if you've got a vector in the direction X, if you apply A, you get another direct vector in the direction X, but it's stretched or shrunk by a factor of lambda, that is the eigenvalue. So how do we find eigenvectors and eigenvalues? Well, if you think about this equation I've just written, if we rearrange this, this is the same as saying that A minus lambda times the identity matrix times X is 0. So in other words, X is in the null space, or in the kernel, of A minus lambda I. So I should have said X, which is a non-zero vector, is an eigenvalue of A if AX equals lambda X. So we're ruling out zero vectors. So if X is in the null space of A minus lambda I, that must mean the dimension of this null space is bigger than 0. It's at least one. There's at least one non-zero vector in there. Okay, so it's got to be a vector space with dimension at least 1. So therefore the transformation can't be invertible, and so we must have the determinant of A minus lambda I is 0. So this is how we find eigenvalues. We write down the equation, the determinant of A minus lambda I is 0, and we solve it for the eigenvalues. So this is an nth order polynomial. So we get n eigenvalues. Lambda 1, lambda 2, up to lambda n. So this leads us to the idea of the spectral decomposition of a matrix. So let's suppose A is a real symmetric matrix. So what does symmetric mean? It means that A transposed equals A. Then if A is real symmetric, then the eigenvalues of A are real, and we can diagonalize the matrix. So that means we can write the matrix as A is Q lambda Q transposed, where capital lambda here is the matrix, the diagonal matrix of eigenvalues of A, and Q is the matrix consisting of unit eigenvectors of A as a columns. So the first column is the first eigenvector, so let's say Q1, Q2, down to Qn. Okay, so Qi is the ith unit eigenvector corresponding to eigenvalue lambda I. So in other words, we have that A times Qi is lambda I Qi, and we have the the length of Q I is 1. Okay, and the matrix Q is an orthogonal matrix, which means that we can write that Q transpose Q is Q transposed is the n by n identity matrix IN. If we think about this product, A is Q lambda Q transposed, in the way we thought about matrix products in the last lecture, we can see that this means we can write the matrix A as the sum of rank 1 matrices. So this is the sum of lambda I, QI transposed. So this is the sum of rank 1 matrices. And if we think about this, if we think about what Q transposed A Q is, this is Q transposed times Q lambda Q transposed Q, which if you think about changing where the brackets are, this is Q transpose Q, lambda Q transpose Q, and these are both the identity. This is just lambda, a diagonal matrix. Okay. So we say that A can be diagonalised. We've multiplied A by an orthogonal matrix, which we think of as a rotation, and we've ended up with a diagonal matrix. So we've orthogonalised the transformation represented by A by changing bases, essentially, is the way of thinking about this. So this concept of this spectral decomposition, it's known as eigendecomposition, is going to be useful to us at various points throughout the module. And I just want to highlight some results that you probably already know. So the first thing I want you to remind yourselves of is that the determinant of a square matrix, symmetric matrix A, is just equal to the product of its eigenvalues. So first of all, we know that A is invertible if and only if the determinant of A does not equal 0. Well, that is if and only if all the lambda i's don't equal 0. They're all non-zero. The other thing we're going to need to know is that A is a positive definite matrix. So I say A is positive definite if and only if all the eigenvalues are bigger than 0. Okay. Oh, and I forgot to say earlier actually that we normally order our eigenvalues. So we normally say that lambda 1 is the biggest, it's bigger than lambda 2, ... and the smallest is lambda n. Okay. So A is positive definite if and only if they're all positive. In that case, because they're ordered, it just means that lambda n is bigger than 0. Okay, so how do we prove this? Let's just see the proof. Let's first of all suppose that A is positive definite. So what does that mean? Well, that means that for any vector Q, we have that Q transposed A Q is bigger than 0. Well, let's let Q be the unit eigenvector corresponding to the smallest eigenvector lambda n. Okay. Well, in that case, what is A times Q? Well, it is just lambda n times Q. So we get lambda n Q transpose Q. Well, because Q is a unit vector, eigenvector Q transpose Q is 1, so this is just lambda n. So sorry, we're proving A is positive definite here. So sorry, it's positive definite if Q transpose AQ is bigger than 0. Okay, so I get strictly bigger than 0 here. So lambda n must therefore be bigger than 0. Let's now suppose that all the eigenvalues are positive. Can we prove that A is positive definite? Well, because A is symmetric, we know we can write A as Q lambda Q transposed. So let's suppose that X be any vector that's not 0. Then if we let Y be Q transposed X, we know that Q is an invertible matrix, it's orthogonal, so it must have a kernel that is 0, contains 0 only, its multiplication must just be 0. So Q transposed X must also be non-zero. Thus, X transposed AX, well, this is X transposed Q lambda Q transposed X. If we substitute X for Y, we get this is Y transposed lambda Y. Now, because lambda is a diagonal matrix, we can see this is just the sum from I equals 1 up to n of lambda I yi squared, or yi are the components of the vector y. And because all the eigenvalues are positive, we can see that this must be positive. So we must have that A is positive definite. Finishing the proof. So just finally then, I just want to remind you that this spectral decomposition we often use to find what we call matrix square roots. So let's suppose A again is symmetric and positive definite. We can write A as Q lambda Q transposed, where lambda is the diagonal matrix of eigenvalues. Okay, and 0 is everywhere else. And we know that lambda n must be bigger than 0. So this form allows us to find various matrices easily. Okay, so first of all, if P is some positive integer, it's fairly easy to see that A to the power P is just Q lambda to the power P Q transposed. Okay. If you think about it, when you write this product, if you've got Q lambda Q transposed times Q lambda Q transposed times Q lambda Q transposed, when you move these brackets, you're going to get all these terms down to the identity, and you're going to get the form as claimed. We can also write the inverse of A quite easily. This is going to be Q lambda inverse Q transposed, where lambda inverse is still a diagonal matrix, but now on its diagonals it has 1 over all the eigenvalues. So first entry is 1 over lambda 1, down to 1 over lambda n. And because we assumed that A was positive definite, all the eigenvalues are positive, so we can divide 1 by them, and these are all finite still, and so this is an allowable thing to do. So we just check this. If we get A inverse times A, well, this is Q lambda gamma inverse Q transposed times Q gamma Q transposed. So we get Q gamma inverse gamma Q transposed. So we get Q transposed, which is the identity. So another matrix we can find is the square root of a matrix. So let's have A to the half. So this is the A, say matrix square root of A. So why do I say it's a matrix square root, not the matrix square root? I say A because there are many matrix square roots. This is just one particular choice. Okay. So if we let A to the half be Q lambda to the half Q transposed, where lambda to the half is just what you'd expect, square root of lambda 1 down to the square root of lambda n, then this behaves as you might expect. So if we do A to the half times A to the half, we're going to hope this equals A, right? If we multiply square root of x times square root of x, we hope to get x. So let's just check this. This is Q lambda to the half, Q transposed, Q lambda to the half, Q transposed, which gives us Q lambda to the half, lambda to the half, Q transposed, which gives us Q lambda, Q transposed, which is A. Okay, so it behaves like we expect. So this is the only symmetric square root of A. So let's say A to the half is the unique symmetric square root of A. Sorry, the square root's not unique, but it is the only symmetric square root. Okay, so hopefully all of that is familiar to you. You've seen it all before. In the next video, we're going to talk about something that may not be familiar to you, called the singular value decomposition. The idea behind the singular value decomposition is that we generalize the spectral decomposition we've seen here to general matrices that don't necessarily have to be square or symmetric.